speaker is Shelby Kimmel from MIT, and we gotta say a few words. So Shelby did her bachelor's project with Bill Wooters. I think that's a very early introduction to the field of quantum information, and has now been doing a bunch of different pieces of work, both on algorithms and on information theory. And today she'll tell us about the robust characterization of quantum processes. And we're planning to go for dinner tonight. If anyone wants to join, just get in touch with me.
Thank
welcome.
You. Yeah, thank you, Matthias, and thank you also to Matthias for inviting me here. It's really nice to be here and to be getting to meet some of you. Can you hear me? All right. Okay. Yeah. So as Matthias said, I've done a couple of different projects. So today I'm going to be talking about process tomography, but I'm also happy to talk about algorithms and any other topics. So I'm getting my PhD at MIT, working with Eddie Farhi, but the work that I'm going to be talking about today I did while doing these internships at BBN, which is the other Cambridge-based company, where they have a quantum computing effort there and a couple of theorists and also some experimental work that I will talk a little bit about at the end. So today I'm going to be talking about robust characterization of quantum processes. And please interrupt me with questions if they come up. So I think everyone in the room is interested in quantum computing, and I don't need to motivate why we might want to have a quantum computer. So maybe a more relevant question is, if we all like to have a quantum computer, why don't we all have them? And the simple answer is that our current implementations have too many errors. So in order to scale up our quantum computers, we need to somehow deal with these errors. We need to get rid of them, improve the performance of our system. But in order to fix those errors, first we need to know what they are. And so potentially if we can better characterize the errors that are occurring in our quantum computers, we can build better quantum computers. So you might here look at the error in your system. So here the error is this kind of box E. It's some quantum process that's occurring in our system. And you might be able to, if you could actually accurately characterize that error, you'd see that maybe in a certain system you had a depolarizing error. And so that would suggest that in order to improve that error, you might need to cool the system down, because you might know that depolarizing errors in your system are caused from thermal noise. Or if you could characterize the error process and find that you were actually getting some kind of extra rotation in a lot of your gates, then you might, because of your system, know that that's caused by some kind of stray magnetic field. And so if you put more magnetic shielding into your system, you could potentially fix these errors. So, but unless you really know what those errors are, it might be hard to target improvements. Characterization of errors is also really important if we want to be able to scale up our computers, because ultimately we're going to not be able to get rid of all errors, but we're going to be using error correcting codes to deal with some errors. And all of our error correcting codes make assumptions about the types of errors that occur in our systems. And so we want to be able to check that the errors that are actually occurring in our system are the ones that we can correct. So you might look at your errors and find that actually in your computer you tend to have some kind of non-local correlated error. Well, that would be very bad for error correcting codes, because most of them assume that somehow your errors are local and are not correlated. But we want to at least be able to check that the errors in our systems can be corrected with codes. So from several different aspects, being able to characterize errors in a quantum system can help us to build better quantum computers. But it turns out that many of the standard techniques for characterizing processes in quantum computers are subject to systematic errors. So basically these procedures assume that you can perfectly prepare a state, or at least you perfectly have perfect knowledge of the state that you can prepare in your system, that you can measure the state of the system perfectly, or at least have perfect knowledge of the measurement that you do. And also, if you're trying to characterize some process E that you care about, there are other gates that you might want to apply, and these procedures assume that you can do all of those perfectly as well. By making all these assumptions, in any physical system, basically none of these assumptions are true. You basically don't have perfect knowledge of state preparation, measurement, or other operations that you apply. And because of that, the results of your process tomography or process characterization procedure are going to be inaccurate or even produce invalid estimates. So your reconstructed process might be a process that's not even allowed by, is not even a valid quantum process, even, outside of just statistical fluctuations. This is just like a systematic error because of your procedure. So we say that procedures that are like this, that make these kinds of assumptions, and these assumptions then lead to these systematic errors, we say that these procedures are not robust. So in this talk, I'm going to be talking about procedures that are robust. So it turns out that even if you don't have perfect knowledge of state preparation or measurement or other operators that you apply in your computer, even without knowing all that, you can still actually learn a lot about a process in your quantum computer. So there are a couple of different techniques to do this process tomography or process characterization. So gate-set tomography procedures are kind of a way of getting around this, where you basically just don't assume very much about your system at all and try and characterize many quantum processes all at once. These are some really nice techniques, and I'll maybe touch on them a little bit towards the end of the talk. But for now, I'm going to be talking about kind of a different group of robust procedures called randomized benchmarking. So these randomized benchmarking procedures have been around for a couple of years now, and they've become actually pretty popular with experimentalists. It's very common to see people claiming, we have such and such fidelity based on randomized benchmarking experiments. But it turns out that while they are robust, they don't make assumptions about state preparation and measurement, et cetera, they are very limited, these randomized benchmarking procedures. So instead of being able to characterize a lot about this error process that you care about, you can only characterize one parameter of any process. And instead of being able to characterize any process that you want, you can only characterize one type of process. So first of all, this one parameter, it basically just tells you if you have an error. It doesn't really tell you, it doesn't give us the type of information that we'd really like about, is it a depolarizing error? Is it a rotation error that we really need to be able to improve our systems? So what I'm going to show in this talk is that actually within this randomized benchmarking framework, I'm going to explain what randomized benchmarking is soon, that instead of just being able to characterize one parameter, we can characterize almost a complete characterization of any process, any quantum process, and not just one type, but any process that we want. We can basically do full characterization. And in doing this, we inherit kind of this robustness of randomized benchmarking, so we don't need to have perfect state preparation and measurement. And in addition, we can efficiently test the performance of a universal gate set, which, depending on time, I might or might not get to talk about. Okay, so any questions on kind of the setup so far about robust versus not robust? We'll give some examples soon, but feel free to ask questions. Okay, right. So, was there a question? No. Okay. Right, so I'm going to discuss how a standard process characterization technique works and where we get these systematic errors that I've been harping on from. I'm going to then introduce randomized benchmarking and discuss how that type of procedure normally works, but why, in the past, it's been so limited in its use. And then I'll discuss how we're able to use these randomized benchmarking techniques to get a lot of information about any quantum process. Okay, so just to quick review, a quantum process is any CP-TP map, so completely positive and trace preserving. There are many, different classes of quantum processes, so unitary, depolarizing, amplitude damping, so on. One of the key things about quantum processes is that if you want to be able to characterize the full process, there are an exponential number of parameters, so order 16 to the n free parameters for an n-qubit quantum process. So really fully characterizing a quantum process can't be done efficiently. Okay, so standard process tomography, how does it work? So generally, a process doesn't act in isolation. It acts on a state, and in order to figure out what it does, you have to measure afterwards. So generally, you just prepare a state, like the zero state, act on that state with the process, and then measure. So this is kind of this idealized situation where we have, we know we're preparing the zero state, we know we're measuring in the 0-1 basis. But in reality, we don't actually prepare this zero state. Really, there's some errored process that occurs. But we can think of it as a perfect preparation of the zero state followed by some process here this lambda naught that characterizes the error in our state preparation. And likewise for measurement, that instead of perfectly measuring in the 0, 1 basis, we have some error process that occurs before. So now you can immediately see there's some issues. If you are assuming that you're preparing the state 0 and measuring in the 0, 1 basis, the thing that you're characterizing is not E, the thing that you wanted to characterize, but it's actually E sandwiched with these errors. So that's problem 1. We're not really characterizing the thing that we want to characterize. Problem 2, and this is really where things get nastier, is that now if, in order to fully characterize E, we can't just prepare the 0 state. We have to see how E acts on many different types of input states. So if you say prepare the plus state and try to measure in the plus minus basis, now the plus state likely has a different error associated with it. So when you prepare the plus state, now you get a different error, lambda plus, that occurs, you can think of as occurring immediately after the state preparation. So now you have the thing that you're trying to characterize, not only is it E sandwiched between errors, but these errors change according to your state preparation and measurement. So this is almost like the definition of a systematic error. It's when something that you're trying to characterize changes according to your measurement setup. You basically want the thing that you're measuring to be independent of the measurement knobs, but here we see that it's very dependent on the knobs that we turn. And so if you try to reconstruct E when your measurements and state preparation are actually of this form, you end up getting very inaccurate results. You end up getting systematic errors. Things don't look very nice. Okay, so one of the ways to get around this is to say we're going to just fix our state preparation and fix our measurement. And now we're going to apply this process that we care about multiple times. So now you can see, even though there's this error term here and this error term here, if we notice any change in frequencies between experiment 1 and experiment 2, we know that that wasn't caused by any state preparation or measurement difference. It could only be caused by our process. So in this way, you can start to isolate the process that you care about from the state preparation and measurement, which you don't care about, because really, we don't really care how well, for now, we don't care that much about how well you can prepare or measure. We just care about what errors are occurring in between.
Is it reasonable to assume you can glue two E's together without any problems in the middle?
Yeah, so kind of however fast you can apply your gates, or maybe there's some lag time in between gates, but that lag time kind of gets subsumed into the whole process that you characterize. So you kind of apply it as it would be applied in the quantum computer, and then that whole kind of process all gets lumped into one process, including any lag time that might be around it. Did that answer your question? No? So suppose E is you're trying to apply a Hadamard. And you apply a Hadamard, and then you wait a second, and then you apply the next Hadamard. So the process that you'd be characterizing is the Hadamard plus, kind of composed with whatever process occurs during that wait time. But you kind of care about what happens during that wait time, because if you have to wait a second before every gate that you apply, you want to know what errors are occurring during that wait time. So yeah, even though there's a gap here, that in time it's actually immediately following. Each one immediately follows the next one. Okay. So you can try and do something like this, and you can start to isolate your state preparation and measurement from your process. But you can't get all of the information you'd like to get about E from this type of setup. And just a simple example of that is if you happen to prepare your system in an eigenstate of E, then basically you're only going to see how E acts on this one eigenstate. You're not going to see the full picture. And to really characterize a process, you need to see how it acts on many different states. So in randomized benchmarking, the random part of it is right before each process that you're trying to characterize, you insert a randomizing unitary. So each time you do one of these sequences, you pick a unitary randomly, at random and apply it right before your gate. And that has the effect of essentially you're putting in a random state right before each time you apply your process. So if you can see how E acts on all these random states, you get a very good picture of the total action of E. And then at the end, because now you're basically in a random basis, you have to do some final unitary to recover to put yourself into a basis where your measurement makes sense. So for randomized benchmarking, people have run these types of experiments, and you see that no matter kind of what your state preparation and measurement is, you get an observable that decays exponentially in the number of, in the sequence lengths. So in the number of times that you apply E, bracketed by these randomizing operations. And now this decay constant just depends on a single parameter of your process. And that single parameter, I remember I said at the beginning that randomized benchmarking is very limited because it can only extract a single parameter. So the decay constant of this exponential is that single parameter that you can extract from a randomized benchmarking procedure. Okay, so you might have guessed I've been talking about errors this whole time, that these randomizing unitaries that you want to apply before each time you apply your process E, all of these randomizing unitaries also have errors. So that's kind of problematic. Like we're trying, we've been doing all this stuff to get away from these errors that might be occurring, but of course we can't assume that we can apply these unitaries perfectly. They also have errors. And basically that has been what his previous randomized benchmarking experiments basically didn't really know how to deal with these errors. And so because of that, you were very limited in the types of processes that you could characterize. You couldn't stick anything in here because that error basically mixed things up too much, and so you didn't know what was going on. So previous randomized benchmarking experiments, they could only extract this single parameter from this exponential decay. There were also the errors on the unitaries made it so that you basically couldn't characterize anything except for the error on the randomizing unitaries. That was kind of the only type of error you could characterize. So we'd like to have a better way of dealing with the errors on the randomizing unitaries. Okay, so any questions before we move on? Yes?
One parameter you can extract is essentially this Clifford map.
No, it's the average fidelity of the process to the identity. So I'm actually going to explain that in the next slide. Okay, so I said we apply these randomizing unitaries, but really instead of applying just a completely random unitary, you apply a Clifford. And the Cliffords have this really nice property that they're unitary to design. So that means that they basically have the same randomizing properties as if you were choosing a totally random unitary. But Cliffords are nice because we can simulate them classically, and because you can sample from them efficiently. So instead of choosing a completely random unitary, we're going to choose a Clifford at random, so some random Clifford CI, then apply our unknown process, and then apply the conjugate transpose of that Clifford. So this whole thing here is called a Clifford twirl of the map E. And it has the effect of simplifying this very complicated process. E, I said it has an exponential number of parameters, and it simplifies this complicated process into a depolarizing channel. So a depolarizing channel is just controlled by a single parameter, P. So, and this parameter P is related to the average fidelity, which is basically how well E preserves states on average. Basically, it's a measure of how close E is to the identity. Okay, so now because this depolarizing channel has such a simple structure, you can imagine when we're now composing this multiple times, which is what we do in a randomized benchmarking experiment, you're going to get a very nice decay. Okay, so this is kind of just a notation slide. So again, we're kind of reading left to right in time. So if we want to characterize our process E, every time we come across E, we want to do this twirl. So we're going to apply a random Clifford CI, and then afterwards apply CI inverse. And so whatever you see in the red bubble is going to be what's being twirled. So all you have to remember is that once a process is twirled, we've converted into this very simple depolarizing channel. So we've lost a lot of information about E, but made it into something very simple and so very easy to characterize. And it turns, even though this is not a perfect Clifford twirl, by repeating this many times and each time choosing a Clifford and then averaging the results at the end, we can approximate a Clifford twirl with arbitrary accuracy. So then our original procedure that looks something like this, with state preparation, some randomizing operation, the process we care about, etc., we can kind of write it in this way. So we have a random initial Clifford, the recovery Clifford to turn this guy into a twirl, the next random Clifford, and so on. And here, even though I've written it as two separate Cliffords to kind of keep track of which is twirling what, this is just going to be applied as a single Clifford. Okay, and then doing this, you just get as you do multiple twirls, you're just getting multiple composed depolarizing channels, and you just get a very nice exponential decay that just depends, the parameter of the decay depends on the average fidelity of your process to the identity. Okay, so now that was just more in detail, the standard randomized benchmarking. So now we want to be able to extract somehow more information. But because this twirl is so limiting, it basically destroys so much information about E, we don't have a lot of options. Either we can get rid of the twirl, do some kind of different procedure that maybe doesn't kill so much information about E, or the other option, and this is what we're going to go with, is we're going to stick something extra inside of the twirl. Because we like these twirls, we get these nice exponential decays that are very easy to fit experimentally. So what we're going to do is we're going to throw an extra Clifford into the twirl. So this is a little bit confusing. These CIs and CIJs, these are random Cliffords that we choose, but now this CX is fixed. It's not chosen randomly each time. CX is just a fixed Clifford that we're going to make sure ends up inside the twirl with our process. So, and again, even though I've broken this block up into 3 separate Cliffords to keep track of what twirl is going with what, we apply this whole gate as one single Clifford. Okay, so what is this bias? How much can we learn by sticking in a Clifford along with our process? It turns out you can, first I should say, so remember here, whatever's in the twirl, we learn the average fidelity of whatever's inside the twirl. So now that CX is also inside the twirl, what we learn is the average fidelity of E to CX dagger. Okay, because that's what we have inside the twirl. And in standard randomized benchmarking, you get these very long decays. You can get sequences of length maybe 100 because the process E is often very close to identity, but now E combined with some random Clifford it probably has average fidelity that's very low. So you often get these very short decays where they decay off, after sequences of length 4. So it's a little bit more of a challenge to extract parameters from these decays. Okay, so how much can we learn now we've been able to, I've shown that we can insert extra Cliffords into the randomized benchmarking sequence. So what can we learn? So this is a representation of a quantum process. So a quantum process has about 16 to the n free parameters. So we've put them in a matrix here. This is the Pauli-Liouville representation of a quantum process. So this is a nice representation because if you have composed processes, you can just multiply the matrices to see how the combined process behaves. And the top row is fixed by trace preservation constraints. But the rest of the matrix is basically free. You can choose all the parameters, and can have a valid quantum map as long as the rest gives a completely positive map. So we have our process. We could combine it with a Clifford and learn the average fidelity of our process to a Clifford. And it turns out that information is enough to allow us to estimate this complete block here. So this is the unital block of the process. So it includes basically all types of processes except for amplitude damping types of processes. So this means we can characterize almost anything you would want. And if you're familiar with amplitude damping processes, those are the types of processes where you're basically, your process is actually kind of performing a measurement, or your process is actually kind of doing some kind of state preparation. And those are the kinds of things that we can't characterize. But anything else that's like a unitary process, a depolarizing process, we can pretty much characterize any of those parameters. So we can learn an exponential number of parameters about the process. So why is this the case? So there's a very simple linear algebra fact that if you have a set of vectors that span a subspace S, and you have some extra vector u, and you'd like to learn its projection into S, then you can just take the inner product of your vector u with all of the vectors in V, and that's sufficient to learn the projection of u onto S. And so basically, we showed that the Cliffords span the unital block. So if we want to learn the projection of some process, E, onto the unital block, it's sufficient to basically take the inner product of our process with a set of Cliffords, because Cliffords span this space. So in taking that average fidelity of our process to Cliffords, that is essentially like taking the inner product of our process to those Cliffords. And so from there, we can reconstruct this unital block. And so the fact that the Cliffords span the unital block, it's not a very difficult thing to show, but we don't think it's been known before, and it's kind of a nice fact. Okay, so I've told you now we can use these same randomized benchmarking procedures that are pretty nice and easy to use, and experimentalists are kind of comfortable with and like to use them in order to be able to learn this whole block, so a lot of the process. But I said there was a second challenge, and that was that our randomizing operations have errors too, and that we somehow need to deal with that. So remember, these are the randomizing operations, these random Cliffords that we apply in between our process. And remember, I said this, even though I've written it as 3 Cliffords, it's really, when in the computer we apply it as a single Clifford. And so every time we apply a Clifford, we can think of it as if we have applied a Clifford perfectly, and then there's some error process that occurs afterwards. So now it looks kind of like we're back to where we were at the beginning. Instead of being able to characterize just E composed with CX, now we have this error that's in the mix. And so we're not characterizing the thing we want to characterize. There's this error term that's affecting things. And for now, we'll assume that every single Clifford has kind of a similar average error. You can get around that assumption, but it's much easier if we assume that this error is the same for now. Okay, so to get around this, we're just going to take out our process that we care about, and that is going to allow us to fully characterize the Clifford error. Right? We can go through and change all these overlaps, change these Cliffords that we compare now the error process to, and that's going to allow us to basically get an almost complete picture of this average Clifford error. So what can we do? We have this, we can learn the unital block of the average Clifford error. For some process that we care about, we can learn the kind of the unital map, the unital part of the combined process of Clifford error plus composed with our process. And because in this representation, composition is equivalent to matrix multiplication, if we could somehow invert this error process, we can act on the inverse on this guy and learn just E, which is this whatever process we've been trying to characterize this whole time. Okay, so can we invert the error process? So there are 2 issues. The first is that this column here, we don't know what that is, so that could affect the inverse. The second thing is this might not have an inverse. Not all matrices have inverses. But it turns out that in practice, neither of these is a concern. So first of all, not knowing this column is not important because we're assuming the process is trace preserving. So the top row is going to be zeros. And so whatever is in that first column just kind of hits a bunch of zeros, and so it ends up not mattering what it is. And in addition, for most cases that you care about, you'd already have pretty good Cliffords that you're trying to apply. If your computer is really terrible, this isn't going to work. But assuming your Cliffords are not terrible, this gate or this process will almost always be able to be invertible. It only won't be invertible if it's completely depolarizing. And if you have a completely depolarizing process, then you're kind of screwed anyway. So it turns out that we can do this. We can invert this process and so get the complete unital characterization of E, which is the original thing that we wanted to learn. Okay, so also at BBN, we decided to try this on a real experimental system and see if this works. So the whole goal of all of this was to try and show that if you do a procedure like this, you can potentially decrease the amount of systematic errors in your estimate of some process. And so we were able to work with, this is a superconducting qubit system. This chip contains 3 qubits, although for our purposes, we were just working with a single qubit. And it's a pretty good system. They are able to perform a universal gate set. So yeah, so we tried to test this out and see if, in practice, we could get better estimates of our process than you can with standard tomography procedures. So how do you tell if your process is good? So in general, this is kind of hard, but one way to test for systematic errors is to see if your reconstruction is not a valid process. So as I said at the beginning, a valid quantum process is trace preserving and completely positive. So if you get a reconstruction that is not trace preserving or is not completely positive, then that's a sign that there's been some kind of systematic error. And that's after you've taken into account of statistical noise that might be in your measurements, you'd still like your process to be completely positive. So in particular, if you look at the Troy representation of any quantum process, the Troy representation is kind of an isomorphism between states and processes. And so we know that for valid states, we must have all positive eigenvalues, in particular eigenvalues between 0 and 1. And so also in this Troy representation of quantum processes, we must have all positive eigenvalues between 0 and 1. So what we can do is we can test for our reconstructed map from this whole process, from this whole procedure, we can test and see, do we have positive eigenvalues? And if you see negative eigenvalues, that's a pretty good sign that there's some kind of systematic error in your process characterization procedure. Any questions on the negative witness test? Okay. So we ran this on the superconducting qubit system, and we compared QPT, quantum process tomography. That's the standard setup where you just prepare, act with your process, and then measure. And RBT and RBT no error correction is our reconstruction. So no error correction, remember there were 2 things that we characterized. We can characterize, this is essentially the combined error E plus the Clifford error, which itself is a valid quantum process, so it should have positive eigenvalues. This RBT is after we've inverted the average Clifford error process and gotten just E by itself. Okay, so here on the y-axis is the negative witness. So this is the size of the smallest eigenvalue in the Troy representation of the reconstructed map. And so what we see is for standard process tomography, we get a lowest eigenvalue that's negative. And these error bars come from bootstrapping. And so what these error bars tell you are basically about statistical fluctuations in our data. So we think that up to statistical fluctuations, this standard process tomography procedure definitely has some kind of systematic error because it has a negative eigenvalue. With the quantum processes that we construct using RBT, we see that the eigenvalues are solidly positive. And this is actually what we expect as well. So just like for pure states, the smallest eigenvalue is 0. But for slightly mixed states, you get 0 smallest eigenvalues. For our process, if you had a perfect unitary process, then you would expect the smallest eigenvalue to be right at 0. But we don't expect that our process is perfect. We expect that there's some kind of depolarizing noise on the process. And so we expect that, and that's going to bring the smallest eigenvalue up a little bit. So this is about where we would expect to find the smallest eigenvalue for a process that has a little bit of noise, a little bit of depolarizing noise. So this negative witness test, it definitely doesn't test for all types of systematic errors. There could still be systematic errors that were, and there probably are systematic errors that we're not fully accounting for. But at least for this basic test, it does seem like we're accounting for many of the systematic errors that are leading to bad reconstructions for standard process tomography procedures. Yes?
Reconstructed other eigenvalues, and if what, so what was the method of reconstruction? Was maximum likelihood, Kalman filtering, or what?
So this was just kind of a linear reconstruction. So we didn't put any, yeah, no. Right, because you could put on some extra condition that you'd want your eigenvalues to be positive, and then obviously we'd find all of them are positive, but we're not adding any extra restrictions. We're just doing a kind of a linear inversion and just seeing what happens. Any other questions? Okay. So there was one other result that I mentioned that we're able to, so there's one thing that if you would like to completely characterize a process, you can't do that efficiently. There are an exponential number of parameters that you need to extract. But what's nice about randomized benchmarking procedures is that there is some information that you can extract efficiently. So suppose now that you have a pretty good working quantum computer, you've fixed a lot of your errors, and you're about to perform a computation. But before you do that, you just want to check that everything's working well. Well, you don't want to do complete process tomography on your computer because that's going to take too long. But you just want to go through and quickly check that for your basic universal gates that you're going to be using for your computation, you want to check that they're all performing well. So in that kind of scenario, we can use these randomized benchmarking procedures to efficiently check for errors in a universal gate set. So before we looked at basically an exponential number of different measurement settings, which involved an exponential number of these inserted CXs into the twirls. But now we don't want it. We want to somehow get this information without doing an exponential number of experiments. Okay, so we basically have this one tool. So we're going to use this one tool again to get this now efficient characterization of a universal gate set. So what we can do is we can look at the average fidelity of E compared to this Clifford CX, or I guess compared to CX dagger. And it turns out that just by doing this for now, instead of an exponential number of CXs, if we instead look at just a polynomial number of inserted extra Clifford CXs, that's sufficient to learn the average fidelity of E, not to some CX, but to some universal gate set. So there are not all, in order to perform universal quantum computation, you need more than just Cliffords. So it's very easy if you're trying to check how well is my Hadamard. If E is a Hadamard gate that you're trying to check, you can just compare it to Hadamard. But for universal computation, you need to apply something outside of the Hadamard, something outside of the Clifford group. So it turns out that just by looking at a polynomial number of these overlaps, you can check the average fidelity of your process to a whole set of universal gates. And in particular, you can check the average fidelity of E to any unitary that has a logarithmic number of T gates, which is an extra gate that we often add in to the Cliffords to give universal computation. And this unitary can also have a polynomial number of Cliffords in it. So we can basically check E compared to one of these unitaries and basically check that our universal gate set is performing well. Okay, so this is assuming that we don't have errors. Now that we have errors, again, we're kind of back in our previous situation where instead of characterizing how E performs, we can characterize how E composed with an error performs. But now we can't take the time to completely characterize the error. whereas before we basically reconstructed the map entirely, and that was how we dealt with the error. Now, since we're trying to do things efficiently, we don't have time to completely reconstruct this error. So what we do instead is we just bound the effect of the error. So we just check that the error is pretty close to the identity. And then from there, we're able to create bounds on, given we know that the error is close to the identity, we can create bounds on our estimates of the average fidelity of E. So that's the strategy to efficiently benchmark a universal gate set. Okay, so just to conclude, I showed how we can use these randomized benchmarking procedures to robustly characterize the unital part of any process. And I kind of sketched how you can use it to efficiently and robustly check that your universal gate set is performing well. We actually implemented this using a superconducting qubit system and showed that things seem to work as we'd like. So some questions for future research are, there's this unital part that we weren't able to characterize. Somehow we'd like to be able to access that as well, even in a robust way. Something I'm also interested in is in combining a procedure like randomized benchmarking with compressed sensing, which has been very successful in tomography procedures for states and also processes. And compressed sensing basically allows you to reconstruct like a state or a process more efficiently than you could otherwise. So we could hopefully cut back on that exponential scaling, make it maybe not such bad exponential scaling to estimate a process. And finally, at the beginning, I said that there's these new robust procedures called gate set tomography methods. So these gate set tomography methods are very nice. They make somehow less assumptions than we do in randomized benchmarking. So in randomized benchmarking, we like the average Clifford error to be kind of similar for all Cliffords. And you don't need that kind of assumption in something like gate set tomography. However, gate set tomography, you have to characterize many gates all at the same time. So not only is there kind of exponential scaling in the number of parameters for each gate, but now you have to characterize many gates all at once. So it's definitely not efficient. So I think it'll be interesting to see, kind of depending on what you're trying to do, whether you'd like to do something efficiently, how much information you'd like to extract, what type of system you're using, and where randomized benchmarking will be used and where gate set tomography will be used. And I think there's a lot of room in between. So I think we're just kind of starting to experiment and learn about these robust methods. So I think there's a lot of work to be done to be able to come up with new methods, maybe somewhere in between randomized benchmarking and gate set tomography that can efficiently and robustly extract the information that you'd like to get about a quantum process. So thank you, and I appreciate any questions, or I'll be around until Thursday. So I hope to see many of you around. Thank you.
Is it correct to think that the essential problem of extending, or actually even asking whether the method would work for, or any other would work for dumping, is that you actually undo everything at the end of the operations. You have this correcting unitary, right, at the end.
Yeah.
And this is completely impossible to do when you have dumping, right?
What's dumping?
Dumping is just this how do you call it? Those channels that have this column.
Like the amplitude damping.
Yeah.
Mm-hmm. Well, I wouldn't. So it's not that. It's not the effect of the recovery operation at the end. I would say so. The way this works is that it's because of that repeated application.
But they are all unitary, right? So you may correct it at the end, in quotation marks, to find the reference frame of the total gate, right?
Right.
And if you have and this is for how do you call bistochastic noise actually? Mm-hmm. It works for bistochastic. So my question is why you couldn't extend this type of methods for the other type of errors, right? And my intuition is because of that, but maybe I'm wrong.
Well, so it's not just because of that final recovery unitary. So just the fact that we're inserting unitaries into the middle of the process if you think of composing a unitary and an amplitude damping process, the unitary kills any information about the amplitude damping process. So
You don't get unitary at the end, right? Yeah, okay. Yeah.
or maybe we can continue the discussion afterwards.
Any other questions?
Are there unitaries besides Clifford's that it's practical to implement?
So I've looked, in fact, at instead of doing, say, a full Clifford twirl, you could do a poly twirl, where you randomly choose polys, say, and perform the twirl. And so what's nice about that is that if you were to twirl with polys, you wouldn't kill as much information. So instead of getting this completely, depolarizing channel, you get what's called a poly channel, which is diagonal in this basis. But what's then not nice about that case is that now instead of fitting a single exponential decay, the end result that you have to fit to extract the information, it would be a sum of exponential decays. And in fact, there would be an exponential number of terms in that sum. And even fitting, 2 or 3 decaying exponentials is kind of a difficult problem. So that's kind of why we like this Clifford twirl, because it's kind of good to get rid of all that extra information because it makes the fitting so much easier.
Are there any more questions? Or do we head over to coffee? Thank you.